welcome to Root Causes, the PKI and Security podcast where a pair of industry veterans talk about all matters digital certificates and PKI. I'm Tim Callan, Chief Compliance Officer at Sectigo, and I'm here with Jason Soroko, SVP of Product at Sectigo. How are you doing today, Jason?
Doing great, Tim. Thanks for having me.
So we have another piece of news in the whole quantum computer, quantum apocalypse story. This isn't actually a post-quantum computing story. This is a pre-quantum computing story, if you will, which is, and we're operating off a Schneier on Security article. So Bruce Schneier, as he frequently does, is right near the forefront of in reporting security developments. And in this case, the article is called Breaking RSA with a Quantum Computer. And the gist of this is that Schneier has reported a Chinese paper, and we've looked at the paper as well, where a group of Chinese researchers have claimed that they can build on existing work that's been done and demonstrate that a quantum computer within the parameters of what can be made today could be used to break RSA. That's kind of the capsule summary.
Yeah, that's correct. It's interesting in the article, the way that it's written, that you really do get the sense that the current paper that's been published was the result of some sharp people catching other people's work, identifying some of the mistakes made, and then basically throwing in theoretically what could a quantum computer that exists even today, with enough stable qubits, could it pull it off? And there's questions then still to be asked with this. So it's an interesting state of things. I'm not terribly shocked by it at this point in time.
Yeah, so let's maybe just give a little more detail on this. So there was you and I covered something, and I should have looked it up, but quite a while ago, like a year ago, we did a podcast about a paper that had been leaked, looked like a draft that had been leaked from a European academic called Klaus-Peter Schor. And let's clarify that Klaus-Peter Schor is a different person from Peter Schor. The names sound similar, so people can get them confused, but let's clarify the difference between those two names because that's obviously very important. Klaus-Peter Schor had put out this paper that stated that he walked through a process at the end of which the draft made the contention that it would break RSA. And people looked at it and poked at it a little, and I think the community subsequently decided that this was not sufficient work to break RSA, even though it was illuminating and valuable. And the final version of his paper actually backed off on that claim. So it looked like Klaus-Peter Schor probably came to the same conclusion on his own. However, this group of researchers essentially contends that by following the same process but using a quantum computer, that it is possible to basically build on what Schor said, Schor with an N, said, and that you could break RSA with a quantum computer that has, I'm reading here, 372 qubits. Now, this is meaningful because there's at least one computer today, one quantum computer today with more qubits than that, and perhaps others, and if not, there certainly are others on the way. So that argument, these researchers are making the argument that in theory RSA could be broken, a 2040-bit RSA could be broken using existing quantum technology that humans have today.
That is right. And so we're kind of in a waiting game, right? So the paper is proposing something that's theoretical. Yeah. And somebody's done the math and his proposal saying with even the lowest level of stable qubits,
Yeah.
that it do exist at the moment today. Let's try it out. It's almost like a call to arms.
Yeah.
Let's at least try it out. So we're in a bit of a waiting game, and it's IBM right now who has a stable quantum computer of that level of capability.
Right. The
And so
Osprey computer.
all that's right, all eyes on IBM now to see whether or not they pick up the gauntlet and go with it, and let's see what happens.
Yeah, and in the
But that's
spirit
it.
of throwing down the gauntlet, one of the things these researchers did was they actually did repeatedly factor 48-bit numbers using a 10-qubit quantum computer that they had available, just as a proof of concept to demonstrate that their fundamental methodology was correct. But obviously they didn't have the necessary computer available to run a proper 2048-bit RSA attack. And so, I think, yeah, definitely this could be seen as a challenge to somebody else to try that and see what happens. But, this is meaningful, right? Like among other things, if this comes together, and this is an article, the story I'm certain you and I are going to watch, if this comes together, it pulls forward the Z date, to go to a term that nobody's really using anymore, a long way from what people have been saying even very recently.
Yeah, Tim, we've said a few things in the past that they're not unique ideas to us, but it's worth repeating. And some of those ideas are, hey, Schor's algorithm. I'm not talking about, again,
Yeah,
not the same
right.
Schor, but Schor's algorithm, which is the most talked about algorithm for plugging into a quantum computer in order to reduce time for integer factorization, as an example.
Yeah.
That gets all the headlines and gets all the talk. But keep in mind that there are other ideas out there. They just don't get the airtime. And I think this particular idea is getting some airtime now. And it shows you that it's something that you and I talked about before, Tim, but eureka moments might not even just come out of what has been a very stable linear pattern of development within stable quantum computing, meaning
Yeah.
quantum computers are growing at a linear rate, and therefore we can kind of figure out that in 10 years or a bit less, we're probably going to enter the state where at least Schor's algorithm will probably be able to render ECC and RSA, something we might have to deprecate.
Interesting you brought up ECC, because this is very focused on RSA. And
that's the other
I
piece
don't know if this is equally applicable to ECC, but I believe the answer is no. Is that correct?
That is what they're saying. That is what they're saying. It would take somebody who is going to read through the dense math of the paper
Right.
to really answer that question. But this is the second thing that we've said. It's not only the eureka moments of stable quantum computing, it's also the eureka moments of better math. In other words, something other than Schor's algorithm. But again, the thing about RSA is, integer factorization, the speeding up of factorizing integers is something that makes RSA just that much more vulnerable. And this is something you have mentioned. I was always a little more worried about RSA because there was an extreme richness of studies going on attacking RSA, which always has been sound for so long, especially at the 2048-bit level.
Wow. Yeah.
But it has been incredible. It's like nobody can ever, like, whenever we do have to deprecate it, we're gonna have to give it a tip of the hat, right? It's not that it was a weak algorithm. Incredible.
Right. What else? I mean, what other piece of technology are we using from the 1970s that is considered to be solid and robust? I mean, I guess the basic 1-0 chip architecture, and just so little else, right? It's been such a champion, and it allowed us to build a whole global digital economy with communications networks and financial transactions and retail and just so many things, all of which just simply wouldn't have been possible without RSA. Like wow, it's going to go down in the annals of technology history as one of the great developments for sure. However, nonetheless, yeah, it does kind of feel like we're running out of runway on that one, doesn't it?
It does. Maybe the extremely oversimplified version of that, and I like doing this by risking making errors in what I'm saying, just to make it understandable for everybody.
Yeah.
Solving for just really large prime numbers, right? Integer factorization,
Right.
is a heck of a lot. It's not easy, but it's a heck of a lot easier than for solving for those bloody points on an elliptic curve. That's just unbelievably hard.
Okay.
Again, it's factorization. It's something that quantum computers will unravel one day, presumably. But that's why you have RSA 2048 versus ECC 256 as an example. The bit lengths are just so much smaller because of the fact that it's not necessary to have such a large bit length in ECC. It's just a much harder thing to solve. And some of the algorithms that are coming out that are not necessarily Schor's algorithm, I'm not surprised that they are specifically targeting RSA. And in fact, Tim, we might have a podcast down the road where we can talk about, highlight maybe the top 5 or 6 RSA attacks that are out there in the world, and because they're actually mathematically quite interesting.
That's good. I like that. So let me ask you this then. Do you, hypothetically, let's suppose that this whole thing has some legs and some smart people go and poke at it and they realize that, holy smokes, we can do this, right? Let's suppose that IBM comes back and says, yup, did it. Here's the demonstration. At that point, do we all switch out all of our crypto to ECC? Is that the next step?
It might be, but I will tell you this. There's a couple things that come to mind, right? A couple things. One of the first questions I would ask, that maybe you would ask, Tim, and some others would ask, is what are we talking about here? Does it take a current quantum computer, like from IBM? Will IBM come back to us and say, we were able to unravel or decrypt a certain small block of ciphertext, and it took us 6 months to a year to do it, or it's going to take us. We know we're cracking it, but we know exactly it's going to take us 11 years, right? Rather than a million years, right?
I think that's a huge difference, right? That's something to understand. If they say, look, we know we're cracking it, but it's going to take 11 years, then maybe nobody gets too freaked out. But if they say we can do it and we can do it in 6 months, then even if we go, well, there's not a lot of secrets that are going to be worth grabbing and decrypting, and there are very few computers in the world that can do this, possibly as few as one today. But what's that going to look like in a year, right? And then you go back to or in 2 years or in 4 years. And then you go back to your whole harvest and decrypt scenario. And we did a whole podcast just on this, which if you want to, understand that phenomenon, go listen to that podcast. But then I start to say, well, geez, man, if my secret is still going to be a secret in a year or 2 years or 4 years, I have a problem. And I have a problem today. And so people are walking around throwing out these dates. Got to be all switched over by 2032,
Yeah, Tim.
It seems to me like it's more like got to be switched over now, right? And because harvest and decrypt is a realistic risk for lots of kinds of secrets.
That is true regardless of any of these eureka moments that you and I will be reporting on until one day we have to deprecate these things. And so doing that exercise of the inventory of what secrets do I have that are being recorded right now, that if they were decrypted, 10 years from now, 5 years from now, a year from now, and put them in that kind of level of prioritization, that is an excellent inventorying that you can start doing right
Yeah.
now. Hey Tim,
Yeah.
I have one other thought I'd like to share about this.
Please.
And again, it's about a consistent message that I think we've been giving. We've been talking about hybrid certificates as a bridge between classic cryptographic algorithms and the future post-quantum algorithms, right? Quantum
Mm-hmm.
resistant algorithms. And I just want to let everybody know, we've said this before. It's especially worth repeating on this particular story, and that is the fact that it also allows you using the usage of hybrid certificates also allows for the agility, the ability to move between cryptographic algorithms, between RSA and ECC. So
Yes.
there might even be reasons to start using hybrid certificates now just to be able to move in. Who knows? There may be a period of time, Tim, where we all have to knee jerk react
Yeah.
away from RSA and move to ECC. Hybrid certificates will be a great way of bridging systems that are hard coded to RSA and essentially use ECC. It's
Yeah.
such a good idea, and that could be applicable sooner than later.
That is, I think, a very insightful and important point, right? We talk about hybrid certs as if the two ends of the fork are always a pre-quantum, an existing current KEM, and a post-quantum, right? Algorithm. But there's no reason why that has to be, why a hybrid cert's just a hybrid cert. You could have any two things on the branches. I don't even know if it has to be two, right? But you could have any set of things on the branches. And if we find ourselves trying to, in a situation where we're nervous about RSA as a foundation stone, there is no reason why hybrid certificates couldn't have utility in advance of that in order to allow us to swap over to ECC in a hurry in the event that that's what we needed.
Exactly. None of us
Now,
has a crystal ball to know exactly which
right,
which eureka story is going to make us all have to jump, but something will eventually. And so,
right.
getting your hands dirty on it now, that's such a good move.
Now, even then, though, like hybrid certs, I'm not sure what level of the software support is for hybrid certs in a private CA scenario, but I wouldn't count on the fact that my stuff is going to use a hybrid cert correctly, right?
No,
So I'm not sure you can take your hybrid certs and just roll them out and have them work today. Furthermore, you definitely can't get hybrid public certs because they're just not allowed. And so those there are still, even if someone, if a CISO is listening to this podcast right this minute and says, good golly, we're in danger, I'm going to go do this today. I don't know if you can do this today. I think the industry has to do some work before you're even able to do this.
right. I would say that it starts even at the HSM level,
Mm-hmm.
because all of these things require thinking about, even just a different CA. What kind of devices are doing the consuming? What are they able to consume? There's a really large inventory work that needs to happen first. Where can it apply? How does it apply? And then starting to take a look at that extra set of fields within the X509 standard, uh,
Yeah.
and understanding, how do you issue that? How do my HSMs and how are my vendors covering that? Again, like you say, Tim, in the public trust realm, there's a whole pile of industry work that has to happen.
Yeah.
I am referring very specifically to some private trust stuff,
Yeah.
and don't forget your signing documents as well. Keep your signing systems in mind whenever you're doing your inventory, because they're going to apply just as much, if not more so, at this point.
Absolutely. So, yeah. So anyway, and we talked about certainly my last thought on this is that there, you and I have talked in the past about when people sort of try to calculate the Z date, they're imagining the progression according to the current line that we see going on right now, right? They're almost Moore's lawing it. And that's fine to set sort of a minimum level of progress. But of course, there's the opportunity for there to be much more advanced progress than that as people come up with new methods and new techniques. And that's really the story that we have here. Now, again, this has to be validated, but it's distinctly possible that that turns out to be that that's exactly what happened here. And what that does is that just pulls all those dates in. And there's no way to know if this proves out to be true. There's no way to know that this is the last time this is going to happen, right? There might be someone else, somewhere else, that's editing their paper for publication that's going to pull it in even further. And so you know, we really got to be careful about thinking that these dates are far in the future. They just don't seem that far in the future to me.
No, and you know, Tim, I don't think we've heard the last from the quantum annealing folks, which is an entirely different
absolutely
computing method. You know, there was a great talk at both Black Hat and DEF CON on that. It's funny. I keep saying that Peter Schor's great work on the Schor's algorithm gets all the headlines. There are other things out there, and it's not just this plodding pace of the, you know, more and more stable quantum bits from all the big quantum computer, you know, those folks, IBM, Google, etc., and of course all the competitors at the nation state level in China. But there's also just really good math and the application of math on not just quantum computers or quantum annealing computers, but even on traditional computers. If you and I were to wake up tomorrow and read a paper that says, hey, we've solved RSA 2048, we can decrypt something in under a month, and we can do it, and it doesn't require a quantum computer, I wouldn't even be shocked to the ends of the earth if I heard that in the next little while. I think it's an actual possibility.
Yeah. Okay. So what we have to do doesn't really change. Right? We've got to be urgent. We've got to get these new things in place, and there's a lot of work that needs to happen to do that. And in that sense, it's all the same. But it will be interesting to see what we learn in terms of this particular set of work, right? And whether at the end of the day, it'll be really interesting to see if IBM decides to try this. And we'll definitely keep our eyes peeled to see what happens there.
Absolutely. And when they do, we'll let you know.
All right. Thanks, Jason.
Thank you, Tim.
This has been Root Causes.